Yeah. Second time's the charm, right? Okay, so this little box right here, I'm not going to spend too long going over it, but I like to tell you what works, and I also like to show you what doesn't work, some of the common errors that students type to make. So everything in the left column is legit. It works, right? Hence the equal signs. So these are all properties of exponents that work because we're dealing with what operation? It's underlined. Multiplication, which could also be division, right? Same thing, which means these are factors. So again, I emphasize that as we go. All of those work because we're dealing with factors. So you can kind of take a look at that. Whereas the column on the right, none of that is true because those are terms, which means they're either added or subtracted. So the rules of exponents work with things that are multiplied or divided, factors, not terms that are added or subtracted. So for instance, a plus b quantity squared is not a squared plus b squared. We talked about that. That's binomial expansion. You'd have to like write it side by side and FOIL it out. You cannot just distribute the 2 inside. Second one's really the same rule except the exponent's a half. You cannot distribute the 1/2 to the 2 terms. Same thing here. It's the exact same thing. If you have the square root of a squared plus b squared, it's not a plus b because these are being added or subtracted. It also works with minus sign, okay? Here's one that's pretty interesting. You cannot split up denominators. 1 over a plus b is not 1 over a plus 1 over b. You cannot split up denominators. Here's kind of the second side of that coin. If you do have a plus b divided by a, this is a big one that students try to do. They see that the a's are there and they want to go, they want to divide out those a's and they think they're left with a b. But those don't divide out because in the top, this a is a what? Not a factor. It's a term, yeah? And you cannot divide out common terms, only common factors. So that does not work. If that were a times b over a, which we have right here, yes, now those divide out to give you 1. All right, now here's what you could do if you're interested. While you can't split up denominators, you can split up numerators. So you could say that's a over a plus b over a. It's kind of like the opposite of getting a common denominator. All right, and now a over a is 1, so you could call that 1 over b plus a. But you cannot just divide out the a's. Notice 1 over b plus a is not the same as b. And then this last one here is pretty much the exact same as the first 2 rules. You cannot just distribute an exponent to multiple terms, only multiple factors, all right? So none of these work. Don't ever try them. Don't ever try them. Now I'm going to prove you one of them. A counter example is not just a sample of like maybe countertop options at the Home Depot when you're trying to redo your kitchen. A counter example in mathematics would be an example that disproves something. So in math, it's very often hard to prove something's true because you have to prove it's true for all cases. And all means infinitely many, okay? But it's a lot easier sometimes to find a counterexample, to be that naysayer. Because if you could just find one example that makes it not true, you've mathematically disproven it. And we say it's not true ever. So even if this little equation works for millions and millions of numbers, if there's just one set of numbers for which it doesn't work, mathematically we say it doesn't work at all. Okay? It has to be true for all numbers. So what we're going to do on example 5, and you'll have some of these on your worksheet, it says to provide a counterexample for the claim that a plus b squared equals a squared plus b squared. So we know this is not true. We're going to prove it. Here's how you do it. You draw a line down the middle. Okay, you draw a line down the middle, and you're going to work with each side independently. Now, you're going to come off to the side, and you're going to tell me which values you're going to choose, and you get to pick whichever ones you want. I'm going to start off with 1 and 0, just because they're nice and easy. I don't want to work too hard. And now you plug it into both sides, and you see, hopefully, that they're not the same. So when you plug in on the left, you get 1 plus 0, and you square it, and then you use your dear Aunt Sally's rule, right? 1 plus 0 is 1, so that's 1 squared, and 1 squared is 1. Sweet. Now you plug them in on the right. So you get 1 squared plus 0 squared, and you simplify. That's 1 plus 0, and 1 plus 0 is 1. And clearly this doesn't work because 1 doesn't equal 1, right? Or does it? Oh, it does. Okay. Uh-oh. So if I'm telling you to find a counterexample and you happen to choose numbers that make it true, it just means that this thing may work for some numbers, but you haven't found the ones to disprove it. All right, so you now can take this, pull it off to the side, and say, I now have a collection of something that successfully does not work. Not wrong, it just successfully does not work. So let's try different numbers, okay? How about A equals 2 and B equals 3? Okay, and we'll try it again. So we get 2 plus 3, quantity squared, and now we have to add them first. That becomes 5 squared, which is 25. On the right side, 2 squared plus 3 squared. Now we square them first. That's 4 plus 9, and 4 plus 9 is 13. Ah, ha, 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 ha. Does 25 equal 13? No. So here's what you do off to the side. You say 25 does not equal 13. Okay, and so what you get to do now is you get to make this cool symbol. It's like two double-lined arrows ramming heads. That's the mathematical symbol for contradiction. Okay, which means that that is not an identity. It is not true for all values of x. There are values of a and b, not x. There are values of a and b for which it does work. We already saw that. But if it doesn't work for a single set of a and b's, we say it doesn't work for any of them. So that's not true. So don't ever try that. Don't ever end up with like x plus 3 squared and call it x squared plus 9, right? We just proved that it doesn't work. So don't do that. And then the same goes for all of these right here. None of those work. If you end up with like the square root of 3 squared plus 4 squared, you're going to get excited and want to call it 3 plus 4. Is it? No, because here's another counterexample. That's the square root of 9 plus 16, which is the square root of 25, which is 5. Whereas 3 plus 4 is 7. It doesn't work. So don't do them. So pay attention to these, know the common errors, and avoid those pitfalls. We are done with this section, all right? So we'll stop right there for today. Tomorrow, no quiz. We're going to jump into 1.3, and we're going to spend one day doing 1.3. We're not going to get to all of it, but I'll hit the highlights, and I will only test you Thursday on the stuff that we cover tomorrow and the stuff that we've covered in class. Okay? Sound good? So Thursday's test is kind of by necessity. We're going to have it a little bit early rather than finish the thorough set of notes, but we need to get an assessment in before the official drop date. So, all right. And I'll be here in the morning. Well, tomorrow I have duty in the morning at 8:20, but I'll be in my room from 8 to 8:20 if you need.